probably not as popular as the ones you heard about earlier this week, but we like them ourselves. So hopefully you will also appreciate what you heard today. So it's a great pleasure to have Caroline Roberts presenting her dissertation today. I actually first met Caroline in the summer of 2013 when she came as an undergraduate student for our summer. And that was because her parents live here in the Atlanta area. She was home from college for the summer, heard that we had a program and filled out an application, and I said, sure, come on down. So then we twisted her arm and convinced her to apply to graduate school here, and apparently she didn't have quite enough of us, so she came back, which was lovely, and stayed for a whole 5 years beyond that. Caroline is leaving us in June, to go off for a fancy new job at the University of Iowa, where she will be the observatory director and lab coordinator for astronomy there. So she's got a permanent job all lined up. She's going to go off and be an and I'm very proud of her. She's probably one of the most mature students that I've worked with, and it's been apparent in everything that she's done. So I will stop talking and let Caroline tell you about the very impressive work that she's been doing over the last couple of years. So take it away, Caroline.
Thank you. Thank you, Misty. And I do want to start off with acknowledging Misty for being my research advisor, being on my committee. It's been so wonderful, and I'm so grateful to you for all the work that you've done for me and all the work that you've helped me learn to do. I want to thank all of you for being here today. It means so much to have you here. And I want to thank my other committee members. So Monica Valuri is here with us on the Skype, and I want to thank Mike Crenshaw and Mukesh Damala. Thank you everyone for being here. I want to thank all the rest of the physics and astronomy faculty. And so these are the folks who are the chairs and the administrative folks and all the graduate students. I am very, very grateful for all the work you've helped me do, all the faculty who taught me classes. Many, many thanks to the graduate students and the staff. I want to thank some collaborators of ours, so Dr. Eugene Vasiliev, Dr. Chris Onken, Dr. Eric Emslem, Dr. Michael Fosnaugh. All these people have helped me tremendously, just like my committee members, at numbers of steps along the way. And I want to thank our Team Ben's research group. So that's Merida, Rachel, Justin, and Katie. And I want to thank family and friends as well, some of whom are here today. All right, so a AGN, or active galactic nucleus, is a bright source at the center of a galaxy, and it is light at multiple wavelengths that is not coming from a stellar source. The first active galactic nucleus was observed by Foth and Slipher in the early 1900s, and the spectrum that they obtained had emission lines that were on the orders of hundreds of kilometers per second in width. And a few decades later, Seifert studied a number more of these objects. And in this instance, the widths of the lines were thousands of kilometers per second in some cases. And he also noted that the objects had high ionization emission lines. Now, because of their high brightness, these objects, when they were studied, were believed to be at first within the Milky Way, just because the brightness was so high. But then a few decades later, it was determined that these objects were at high redshift, and so they were coming from outside the Milky Way. And so they actually had incredibly large luminosities. And it was also discovered that there was variability to these sources in some instances on very short timescales. And so this indicates that the source is coming from a very small region and size. And so with high luminosities and small radii, it wasn't really understood what these phenomena could be. And it was a number of ideas were proposed, but it was finally we have come to accept that the reason or the source behind AGN is accretion of a accretion disk onto a supermassive black hole within the center of a galaxy. And we now understand that in the center of every every galaxy, every massive galaxy, there is a supermassive black hole. And not every galaxy is active, only 1 to 10% depending on how you define AGN. But every single one of them has one of these supermassive black holes if they're large enough. When spectra were observed, some of the spectra looked as this bottom spectrum shows. And so we've got wavelength on the x-axis, flux on the y-axis. And this is similar to the spectrum that was observed by Foth and Slipher. Of course, they used photographic plates, but they saw these narrow emission lines of hundreds of kilometers per second. But then the objects that were studied, in some cases, had these broadened emission lines, like the Seyfert-1 object shown at the top there, so much higher velocities indicated by those emission lines. Now let's look at the components of an AGN to determine a little bit why, at least in disk galaxies, we see different spectra like the ones shown here. So we have the supermassive black hole in the center, surrounded by an accretion disk. A little bit further out, we have the broadline clouds. Further yet, the gas and dust torus. And then the narrow line region is within these radii and also further out as well. Now, depending on the viewing angle of the observer of this system, one might see spectra similar to the two on the previous slide. So if you're looking from a more face-on inclination, so closer to 0 degrees, you're going to see both the narrow line region and the broad line region. So we call this a Seyfert-1. In the case of a Seyfert-2, you're looking at a higher inclination angle that's more closer to edge-on, and so you've got the gas and dust torus blocking the broadline region. The supermassive black holes at the centers of galaxies have been found to be linked to other properties of the host galaxy. And this is quite amazing because the sphere of influence of the supermassive black hole, where the gravity dominates, is only at much smaller radii than the regions where these properties still scale. So even once you get out of the supermassive black hole sphere of influence, you're still having these relationships. And for this reason, because this relationship is so important for understanding how galaxies got to be the way they are, we want to characterize and we want to obtain the masses of supermassive black holes as often as we can and in as many different ways as we can. One way of doing this is applicable in one case only, in our own Milky Way galaxy, looking at the proper motions of stars around our supermassive black hole, Sagittarius A star. Now, for another technique, water maser emission. Water maser emission, so a microwave laser, water maser emission in the disk of a galaxy that's viewed edge-on is going to trace out a Keplerian rotation curve. And so the mass of the supermassive black hole at the center can be constrained. What we have here at the top is a diagram of the geometry of a water maser disk. Below it is a spectrum with velocity on the x-axis, intensity on the y-axis, and each of these regions of the spectrum are coming from the portion of the diagram shown at the top. And then we have that rotation curve in the inset of the plot. Now, in reverberation mapping, the response of the broadline clouds to light from the accretion disk is used to probe the unresolved gas within the central region in order to obtain the supermassive black hole mass. Gas dynamical modeling is another technique where the gas is actually spatially resolved in order to determine the geometry of the system and find the supermassive black hole mass. And stellar dynamical modeling is a method where it's very similar to gas dynamical modeling, but the bulk motions of stars are spatially resolved, and this is going to allow us to, again, determine the geometry of the central region and obtain the supermassive black hole mass. Now, a sixth method for finding the supermassive black hole mass was talked about very recently in the news. 2 days ago, we found that the supermassive black hole of M87 had a mass of 6.5 billion solar masses. And what's fantastic is this example from recent news gives us an example of an important technique within extragalactic astronomy, which is comparing the supermassive black hole masses obtained through one method to the mass obtained through another method, allowing us to, for the same supermassive black hole, compare different techniques and understand some of the validities of certain assumptions in each method and sort of cross-check the methods that we're using. And so this supermassive black hole mass of 6.5 billion solar masses was in good agreement with the gas dynamical modeling measurement, stellar dynamical modeling measurement, and the gas dynamical modeling measurement was 3.5 billion solar masses. And so off by, almost twice, and so a sizable difference. And it's important to continue to find these masses in order to cross-check and compare the methods that we're using and understand their reliability. Gas dynamical modeling and stellar dynamical modeling use spatially resolved spectroscopy to trace out the motions of the gas or of the bulk motions of the stars. And so what's shown here at the top is a infrared spectrum of a galaxy, and you can see the absorption line profiles. And at the top above it is a velocity template star, a template spectrum that we then convolve with these Gaussian terms, blurring and shifting the spectrum so that we can best match it to the observed spectrum at the bottom. And so these Gauss-Hermite terms that we use to convolve the spectrum to fit it to the galaxy spectrum are velocity shift, a broadening velocity dispersion, and these higher order terms, so skewness is a left and right asymmetry, which is H3, similar to kurtosis is H4, which is a peakiness factor to the absorption profile or the emission profile. And then we have higher order terms, H5 and H6. And these describe the kinematics of, in this case, the stars, because it's an absorption profile at this particular spatial position. This is a single spectrum, but in stellar dynamical modeling, you want to have spectra from multiple spatial positions across the field of view. Now, I mentioned that supermassive black hole masses are tied to other properties of the galaxy. There are relationships between the supermassive black hole mass and properties of the host spheroid in which the supermassive black hole resides. And so in an elliptical galaxy, that's the entire galaxy. In a disk galaxy, that's going to be the bulge. But so on the left here, we have the supermassive black hole mass on the y-axis, and on the x-axis, we have the luminosity of the bulge. And on the right, supermassive black hole mass on the y-axis, and on the x-axis, the velocity dispersion of the stars in the bulge, so the range of the velocities that are observed. And there's strong relationships between them. The supermassive black hole mass is also linked to the mass of the stars within the bulge. However, here again is shown the supermassive black hole mass on the y-axis and the velocity dispersion on the x-axis, so we call this the m-sigma relationship. Plotted here we have the values for a number of galaxies, where in black we've got the classical bulges, and then we have systems that are barred for both classical bulges and pseudobulges, where a pseudobulge is a bulge that has not been formed through a merger. It's formed through a more secular process, and the bulge is not as compact usually. And so, as you can see, for those barred pseudobulges and also the barred classical bulges, they tend to fall below the m-sigma relationship. And so this begs the question, is it because of an inherent difference in the m-sigma relationship of these objects? Is there really an offset in the slope of these relationships when we break it down by classification? Or instead, is it perhaps a issue with the treatment of these determinations for the supermassive black hole mass or the velocity dispersion for these particular types of objects. And one thing that we will talk about today is the fact that when stellar dynamical modeling codes, so the computer simulation that's used to determine the supermassive black hole mass of some of the galaxies, when a stellar dynamical modeling code that is assuming axisymmetric density profiles is used for systems that are barred, it's going to routinely overestimate the supermassive black hole mass. And so in fact, for these systems that are being treated with axisymmetric codes when in fact they're barred systems, we're going to find that we would expect that their position on these scaling relationships is going to decrease even further in supermassive black hole mass because it's currently being overestimated. And so we might find that there's actually an offset for these barred systems even more significant than we currently see. But the supermassive black hole mass is overestimated by these codes for a number of reasons. One, the velocity dispersion increases in these systems. And this is for a couple of reasons. One, just when a barred system is observed, there's a projection effect. Stars traveling along a bar are going to appear to have a higher stellar velocity dispersion than they really do as they travel along the bar. But also, there's a physical increase. It's been found through n-body simulations that as a supermassive black hole grows in a system or evolves within a system with a bar, the gravitational potential of the system is going to be altered, and the orbits are going to be scattered, and if the velocities are increased from the scattering, you're going to have an increase in the velocity dispersion. Also, when orbits are traveling along a bar, they produce negative H4 values. So this is that peakiness factor that we were talking about to the absorption profiles. And stellar dynamical modeling codes are going to try, or axisymmetric stellar dynamical modeling codes, are going to try to account for this by placing stars on tangential orbits, which is, if they're all going in a tangential orbit, going to do very little to account for the high velocity dispersion that's already there. And so trying to fix one problem, you're increasing another issue, and the supermassive black hole mass to account for these high velocity dispersions is going to need to increase the required enclosed mass. And so when these increases and decreases in these terms are considered, the supermassive black hole mass may be increased by up to a factor of 2. What's shown here are kinematic maps from some of these n-body simulations from Brown et al. 2013. So shown in the top left is a map of the velocity dispersion. So we've got x and y position on those two axes. Same for the second panel is showing the H4 term, that kinematic term. And as you can see, the velocity dispersion is increased and or very high, and in the second panel, the H4 value is very low. And they also ran these simulations for unbarred systems, and they found that the velocity dispersion was not as high, and the H4 value was not as low in the unbarred systems. And then the pink lines show a slice of the kinematics that were taken, where that one-dimensional plot is given in the bottom there with just x-axis position on the y-axis, and then the value on the, or on the the position on the x-axis, and then the intensity of each term given on the y-axis. Okay. So in addition, or I suppose as I've said, one thing that's very useful to do is to apply multiple methods of supermassive black hole mass determination to individual systems, so finding out the mass of a single object from multiple techniques. And so in our case, we're going to compare results from reverberation mapping, stellar dynamical modeling, and gas dynamical modeling. And so targets that can be studied with stellar dynamical modeling and gas dynamical modeling need to be nearby, because we need to be able to resolve the black hole sphere of influence ideally, and resolve the bulk motions of the stars or the gas in the system. But if we're going to compare this mass to reverberation mapping, we need to look we need to study an AGN. And AGN are only 1 to 10% of all galaxies, and so on average galaxies are far away, and so on average AGN are going to be far away. And so there's only going to be a handful of objects for which you can apply both of these techniques to obtain the supermassive black hole mass both ways. NGC 4151 is one such object. It's an AGN that's very nearby, and it is also weakly barred. And so it's also critical to understand the ways in which the use of axisymmetric stellar dynamical modeling codes affect the supermassive black hole mass that is obtained. It's a Seifert 1.5, so this means that the strength of the narrow lines and the broad lines are comparable. And we worked to do a reanalysis of the stellar dynamical modeling mass for NGC 4151, making improvements to the analysis of the data in preparation for the use with a bar-optimized stellar dynamical modeling code. We used the axisymmetric stellar dynamical modeling code of Valerie et al. 2014, but we are directly collaborating with the researchers who are making the new bar orbit superposition code, so Monica Valery and Eugene Vasiliev. And once we are with our analysis done, it will be able to be used with the bar orbit superposition code at a future date. But our reanalysis did a number of improvements to the data set that it has been recognized needs to be done. The reverberation mapping mass for this target was obtained by Benz et al. 2006 and also DeRosa et al. 2018. The gas dynamical modeling mass was obtained in 2008. And as I was discussing, the stellar dynamical modeling mass for this target has been found before, and it was done with an axisymmetric code. And we redid the analysis with the axisymmetric code, making numerous improvements on the ways that the data was treated. For our stellar dynamical modeling, we used an integral field unit because we needed spatially resolved spectroscopy at multiple positions on the sky. So an IFU is going to take the field of view that is being observed, and once it passes through the optics of the telescope, it's going to encounter a slicing mirror, so cartoon and image shown here, and the field of view is going to be broken up into a number of slits. And these slit images pass a little bit further through the optics and pass into the slit, and then encounter the dispersion grating that's going to take each slit image and create a spatially resolved spectrum for each of those slits that can then be placed onto the CCD detector. We did the reanalysis of the Gemini NIFS data, so these were taken in Hawaii on Mauna Kea. And we also considered wide field IFU data, or wider field IFU data. And these were taken from the William Herschel telescope on the Sauron instrument. And the reduced data were provided to us by Eric Emslam. And the data were originally published in Dumas et al. 2007. However, we reanalyzed the data cube and used it for our analysis. So the NIFS data were in the H band. They were collected in 2018. These archival Gemini NIFS data had a field of view of 3 by 3 arcseconds, and our spatial resolution was 0.05 by 0.05 arcseconds, and our spectral resolution was 1.6 angstroms per pixel. The William Herschel Sauron data were in the optical. They were collected in 2004. The field of view is much wider, so 30 by 40 arcseconds. The spatial resolution is about 1 by 1 arcseconds, and our spectral resolution is 4.2 angstroms per pixel. The NIFS observations, there was 252 of them. They were taken on 8 nights in 2008. Along with the data, telluric template star spectra were obtained. And so this is to correct for the Earth's atmosphere absorption. At the same time, velocity template star observations were collected. And so what was obtained was a G, K, and M star template. This is because in the infrared, the spectra of a galaxy is going to be dominated by giant late type star spectra. And then we flat fielded the data, bad pixel corrected, sky subtracted, wavelength calibrated, and a couple other items that I will discuss right now. For our telluric correction, one way that we improved on the analysis, in addition to including this wide field of view data, was to look to use the XTEL core method of Vaca et al. And so in this method, a synthetic spectrum of the star Vega is used to correct for the black body shape and the stellar the stellar absorption features in order to remove any stellar signatures from the telluric template stars. And what's shown in white is that original telluric template star with wavelength on the x-axis and flux on the y-axis. And then above it in yellow is once the features of the A0 star that was observed as the telluric template are taken out. We're left with in yellow just the representation of the Earth's atmosphere. So the absorption from the Earth's atmosphere alone is what's left. A0 stars are often used for telluric correction because they are not going to have very many spectral lines. They're early enough spectral type for that, but they're also late enough spectral type that they're common enough that there will be one near the field of view being observed. Okay, so to step through the reduction so far and say a bit more about the reduction steps that we took at the end, we began with a field of view of 3 by 3 arc seconds that was divided up into 29 slices. The slices were dispersed and placed onto the CCD detector. A spatial rectification was solved for, and then the two-dimensional CCD data was rectified into a data cube. So we've got X and Y position on the X and Y axes, but then in a Z direction we have spectral information. Then the spectra, or what we call spaxels, spatial pixels, were drizzled so that it was and we interpolated so that we then finally had spaxels of 0.05 by 0.05 arc seconds. We threw out some cubes with high PSFs and we aligned and combined them into a final data cube. And this is the final step of our reduction. And to begin our analysis, the first step that we take is we bin the spaxels in a scheme from the Voronoi binning method. And so in this case, we're able to preserve the high spatial resolution at the center, while for the spaxels at the edges that had lower signal to noise, Voronoi binning is going to assign bins such that across the field of view, every bin will have a constant signal to noise. And so at the edge there, the signal to noise is able to be increased. So within these bin assignments, every single spaxel within an individual bin are going to be co-added. And because a stellar dynamical modeling code is going to assume a symmetry to the system, we assign our bins in a symmetric fashion. So once the bins are assigned for only a half plane, we rotate the assignments over to the other half of the field of view. So we're left with one spectrum for each bin that's shown here. The colors here don't represent anything. It's just so that you can distinguish between individual bins. Then, with our data cube binned, we're able to begin the spectral fitting. And so we use the spectral fitting method called the penalized pixel fitting method. And in this approach, template star spectra that have been observed are convolved, blurred, and shifted by Gauss-Hermite parameters. So these are the velocity dispersion, H3, H4 that I was discussing before. template spectra are convolved with Gauss-Hermite terms in order to match the observed galaxy spectra. And so shown at the top, we've got wavelength on the x-axis, flux on the y. The black spectrum is the galaxy spectrum from a particular position in our field of view. And then the red spectrum is the template spectra, a combination of the GK and M star templates convolved with the Gauss-Hermite terms in order to match the absorption profiles and spectrum as a whole of the galaxy at that position. In the center panel are our residuals in green. However, the purple dots mark the spectral wavelengths that were actually included in the fit for determining the kinematic terms. And so there are some high residuals, but for the most part you see those weren't used in the final fit for determining the required Gauss-Hermite terms that represent the kinematics at each position, the position of this spectrum. In the final panel, we have the noise spectrum. This is another way that we improved the analysis of Onken et al. And the NIFS data reduction pipeline doesn't have a good way of carrying through the noise information through the analysis. And so we developed a way to make sure that we had this information for our stellar dynamical modeling. As I mentioned, there's a certain symmetry assumed in stellar dynamical modeling codes. And for this reason, PPXF is able to take two spectra symmetric across the center from one another and fit both of those spectra simultaneously. And so we implemented this point symmetric fitting when we ran PPXF. And when this is done, pairs of spectra are fed to PPXF and the kinematic terms are determined for the positions that those spectra come from. We're left with, we obtain kinematic maps such as these. And so what we have on the left is a map of velocity, so x and y position in arc seconds on the x and y axis, and then velocity dispersion h3 through h6. Any high terms are going to be red, any low terms blue, and anything in the middle for velocity and sigma are going to be yellow and green. Anything close to 0 is going to be yellow and green for h3 through h6. And here we also, or maybe not here, but another thing that we implemented was to include the penalty factor for this penalized pixel fitting method. The penalty factor looks at the noise of the spectrum and determines for any of the higher order terms, places where the fit does not, or the templates used do not significantly improve the fit to the data. And in this case, the higher order terms are forced to 0. And so at the top, you can see the penalty has been set to 0 or no penalty. And so in the h3 through h6 terms, there are some spurious terms that are very high or very low. But then when the penalty is turned on and set to the choice value that we determined, you can see h3 through h6 terms get closer to the yellows and the greens, because in certain instances, it was found from the noise information that the use of those terms was not significantly improving the fit. When we fit our template spectra, we used a G-star template at first, but it was only contributing in 20% of the bins, so we did not include it in our final fit. The K-star template contributed more than 90% of the time, as did the M-star template, so we included both of those in our final run of PPXF. And our results for the NIFS data are shown here. The labels show their identities, and in the center for the errors, we took the output error from PPXF, and although the final PPXF run included both the M and the K-star template, for determining the errors, we ran PPXF for each of the templates individually, so just for the K-star and just for the M-star, and then we took the standard deviation between the results and adopted these values as our errors. In the bottom panel, it's the same as the kinematics in the top, but we have some bins that are masked, and so the white bins have been omitted from our final data set. And these bins are masked at the low radii because there's contamination from the AGN. But at the larger radii, the penalty term is able to give some information about which bins are reliable. And so we included that information and masked some of our fits based on the information from the penalty. We also ran a PPXF analysis for the Sauron data cube. And so, oh, no, I'll talk about that in a second. What we have here are our kinematic results compared to the results from Onken et al. 2014. And so these are the first 4 terms of our results, where in our case we have point symmetrized the spectra, so the bins are symmetric across the center. But in the center here, Onken et al. Originally ran his data cube, which was binned into larger bins at the center than ours were, our data cube was, and binned at smaller bins at the larger radii, a constant binning. In the center, PPXF was run without any symmetry being applied. And at the bottom, however, bisymmetrization was applied. So the output PPXF terms were then averaged across the center as well as to the left and right. And our Sauron results are shown here. So we have our kinematics at the top. Our errors were again determined from finding the standard deviation between the contributing templates. And then our final kinematic maps are masked maps, and this is again from the AGN contamination at small radii. But at larger radii, we know that there's going to be an increased contribution from the disk, and we want to remove any effects of the weak bar in NGC 4151. So we mask bins at large radii where the light from the disk is contributing heavily. Okay, so to recap our analysis with PPXF, we have 2 fields of view, IFUs. One is 3 by 3 arc seconds, one is much larger at 30 by 40, and this is one way that we improved the past analysis of this data set by looking at these large-scale kinematics. We also improved the method of the telluric correction, we included noise information, and we did Warner binning on the data, which allowed us to improve the spatial information at the center and improve the signal to noise at the edges. We included the penalty for PPXF, and we did symmetric fitting so that spectra that were symmetric across the center were fit by PPXF simultaneously. And so this is going to effectively increase our signal to noise, but also when the Gauss-Hermite terms are being determined, it's a compromise a bit between the spectra on either edge and determining Gauss-Hermite terms that best fit both spectra simultaneously. Before we can begin the stellar dynamical modeling, there's one more step, there's one more piece of information that we need. And this is the luminosity distribution of the field of view. And so for finding this information, Misty Benz used a Hubble Space Telescope image where that was also in the H-band, and then the multi-Gaussian expansion package was used in order to take this 2-dimensional surface brightness information and fit it with multiple nested Gaussians that then, with an assumption of the inclination angle, can be deprojected into a 3-dimensional luminosity distribution. Now, these are the 2 pieces of data that we need for stellar dynamical modeling. This is because when you assume a supermassive black hole mass to light ratio, and inclination for your first model run of this computer simulation of your galaxy, if you know the luminosity distribution and you have a mass to light ratio, you can determine a mass distribution of the stars. And with the mass distribution of the stars and the estimate of the supermassive black hole mass, you can construct a potential. And then within your model, orbits are constructed, and these stars within their orbits are iterated numbers of times. And then for each position in the model, the distribution of velocities is measured. So you create a line of sight velocity distribution at each position you're observing your computer simulation galaxy. And then you can fit that line of sight velocity distribution to obtain very similar Gauss-Hermite terms to the kinematics from the actual observations. And so now for one model, we have output kinematics that we can compare to the observed kinematics. And the last step is to iterate. So to do many models for many supermassive black hole masses, many mass to light ratios and inclinations, so that a chi-squared between each of the output kinematics can be computed relative to the observed kinematics, so that the best fit model can be found with a best supermassive black hole mass, mass to light ratio, and inclination. So MassMod, the axisymmetric stellar dynamical modeling code we used, is developed by Valery 2004. In our runs of the models, we use 17,000 orbits for each model run. These are functions of energy and angular momentum. We ran MassMod in two separate situations. One was for the NIFS kinematics along with the Sauron kinematics, that wider field of view. But then we also did it for the NIFS kinematics by itself. We looked at supermassive black hole masses in increments of 1 × 10⁷ solar masses, so 10 different choices of the supermassive black hole mass. Upsilon there is mass to light ratio. We looked at mass to light ratios between 0.2 and 0.5. We looked at 5 different inclinations in increments of 15 degrees. And then we did this 100 models for each inclination, NIFS and Sauron, NIFS alone, so 1,000 final models. And I will share with you now our best fit models for NIFS and Sauron and NIFS alone. So for NIFS and Sauron, as you can see, the observations do not, or the model kinematic outputs do not well fit our observations. They have trouble fitting our observations, especially for the velocity dispersion term. Velocity dispersion for NIFS is shown here. What's at the top center is a chi-squared map of the model fits to the kinematic observations. So along the x-axis, we have the black hole mass that was used for each model. The mass to light ratio for each model is along the y-axis. And then the lines show lines of constant chi-squared, where the minimum of the showing the best fit model is the star at the top there. And so this found a supermassive black hole mass of about 5 × 10⁷ and a mass to light ratio about 0.5. However, we believe that while we omitted bins at large radii in the Sauron data set, there is still significant light from the disk contributing, and so the kinematics of a bar is still present. And as this is being used with a axisymmetric stellar dynamical modeling code, we then chose that our final best fit model would be run with the NIFS kinematics alone. And so our best fit NIFS only kinematic maps are shown at the bottom, which found a supermassive black hole mass of 2.44 × 10⁷ solar masses as our best fit model. The supermassive black hole mass decreased by about half. The mass to light ratio also decreased pretty considerably. Onken et al. 2014 found this as well. They had some large-scale kinematics. It was long slit spectra. And when they included the long slit spectra, they found that their supermassive black hole mass increased by about twice. And so by excluding these larger kinematics, we really do think that we're removing the signature of the bar. Our supermassive black hole mass is within the error bars of Onken et al. 2014, but lower than it. We believe that with the changes that we've made to the analysis, however, this decrease of this magnitude is expected. And then within the error bars of this gas dynamical modeling mass, but between the values for reverberation mapping. So above that of DeRosa et al. 2018, but below that of Benz et al. 2006. DeRosa et al. Just looked at the H beta line, whereas Benz et al. Was an average of multiple lines. Going forward, one thing we want to consider is the possibility of some template mismatch in our data. And so we have in template mismatches where the kinematic results are dependent upon the spectra that were used, the template spectra that were used. And so we had a G, K, and M star template that were observed along with the data set. But going forward, we may want to consider having multiple M stars, multiple K stars, multiple G stars for our fits. And so The IGRIN spectral library is in the H-band. There aren't a lot of template spectral libraries in the H-band, however, so we're considering using this library, but also possibly we may need to use synthetic spectra. Synthetic spectra are going to rely on the assumptions made for the models, though, so we want to stick with observed spectra if we can. With the stellar dynamical modeling mass of Onken et al. 2014, this is the position of NGC 4151 on the M sigma relationship. With our newly determined supermassive black hole mass, the value decreases as is shown here. But last, certainly not least though, is the fact that this is a weakly barred system that is still being treated with an axisymmetric stellar dynamical modeling code. And so we want to treat it with the bar orbit code that's being developed by Vasilev and Valery. But we have made numerous steps to improve the analysis of the data that was done in the past. And we're collaborating with Vasilev and Valery, and we're really excited to use this code. It will be the first code that's able, well, it's one of a few codes that has triaxial density profiles, but it will be the first code able to handle the dynamics of a bar. And 4151 will be one of the first objects treated with a bar orbit superposition code. In the maps that are shown here, in the H4 plot, you can see the low H4 values. In the velocity plot, you can see a twisted isovelocity contour that's really indicative of a bar in this system. It's definitely weakly barred, and we want to treat it with a bar orbit superposition code. 4151 is a really unique object. You're able to obtain its supermassive black hole mass with multiple mass determination techniques. And this is really useful for checking the assumptions made in supermassive black hole mass determination techniques. Now, to perform stellar dynamical modeling, we used the spectral fitting method, PPXF. We also used the stellar dynamical modeling code MassMod. And then we found a supermassive black hole mass of 2.44 times 10 to the 7 solar masses after improving the data set in a number of ways that the data were treated. Thank you guys so much.